In this video, we're going to look at another example of Torricelli's law. So what we're given here is a hemispherical tank with radius 3 meters is filled with water at time t equals 0. At time t equals 0, a circular hole with radius 2 centimeters at the bottom of the tank is opened and the water exits through the hole at the bottom. How long does it take for all the water to drain out of the tank? We're going to apply Torricelli's law. A of y, which is the cross-sectional area of a slice at height y, and dy dt is the rate of change of the height of the fluid in a tank, and as small a, this is the cross-sectional area of the hole at the bottom, g is gravity, and of course y is the height of the fluid at time t. Alright, so let's draw this diagram. So we have a hemisphere, and we have the radius of the slice, which is going to be x here because we're on a coordinate system, and the distance of this cross-sectional slice to the x-axis is just y. So the distance from the top is 3 minus y. We have the radius of the hemisphere, which is 3 meters. So we can now get a relationship between x and y. Why do we need this relationship? Because we need the cross-sectional slice area as a function of y, not as a function of x. So basically, we have the radius of the cross-sectional slice, which is x. The distance of this slice from the top is 3 minus y. And the radius of the hemisphere, which is equal to 3. And we have a right-angled triangle, so we can use Pythagoras to get a relationship between x and y. But we're going to need this relationship later, so we can express the area of the cross-sectional slice as a function of y. X squared plus 3 minus y squared is equal to hypotenuse squared, 3 squared. All right, so we have the Torricelli law, a of y, dy dt is equal to minus a root 2 gy. Now, the cross-sectional slice has an area of a circle, right? It's pi x squared, pi times radius squared, and the radius is x. The radius is an x quantity, is equal to pi x squared. That's because the cross-sections perpendicular to the y-axis are circles with radius x. Now we apply the Pythagoras to get a relationship between x and y. So x squared plus 3 minus y squared is equal to 9. So now we have the cross-sectional slice as a function of y, as a function of height. And x squared, solving for x squared, we get x squared is equal to 9 minus 3 minus y all squared. Let's substitute that in. We get 9 minus 3 minus y all squared. And the area of the hole at the bottom is equal to pi times radius, and radius is 2 centimeters. Let's change that to meters. We're in a metric system, 0.02 meters all squared. This is equal to 0.0004 pi. And this area is going to be, the units are meters squared. So this is the area of the cross-sectional area of the hole at the bottom. All right, so we have a of y, dy dt is equal to minus a root 2 gy. That's Torricelli law. We solve for the cross-sectional slice of fluid at height y to be equal to pi x squared, because the radius of the cross-sectional circle is x. And we applied Pythagoras to get a relationship between x and y. So we get pi times 9 minus 3 minus y squared. And the cross-sectional area of the hole at the bottom, we found it to be 0.0004 pi meters squared. Let's substitute all of this in and get a differential equation. So we have pi times x squared, that's 9 minus 3 minus y all squared. All of this is going to be a of y times dy dt is equal to minus the cross-sectional area of the hole at the bottom is 0.0004 pi, and multiply this by root 2 gy. 2 times g is 9.8, and times y, which is the height of fluid at time t. All right, so now let's simplify this. We have pi times, well, the pi cancels out on both sides, so let's get rid of that, and we have 9 minus, let's open up 3 minus y squared. That's going to be 9 minus 6y plus y squared. And times dy dt is equal to minus 0.0004 root of 19.6 times root y. So if we simplify this, 9 minus 9 is 0. And what are we going to get? Well, we're going to get 6y minus y squared times dy. And let's divide by root y. We're separating the variables at the same time. Root y is equal to minus 0.0004 root of 19.6 times dt. We now have the variables separated. And so what we have is 6y minus y squared. Let me look back on the last page. 6y minus y squared divided by y to the 1/2. We can write root y as y to the 1/2 times dy is equal to minus 0.0004 root of 19.6. We're keeping everything exact. So now we need to integrate both sides, but before doing that, let's simplify the left-hand side. So let's divide it through. 6y divided by y to the 1/2, that gives us 6y to the 1/2. Minus y squared divided by y to the 1/2. 2 minus 1/2, that's 3/2. Y to the 3/2 dy is equal to minus 0.0004 root of 19.6 dt. So now we're able to integrate both sides. Let's apply reverse of the power rule. So add 1 to the exponent, divide by the same. 1/2 plus 1, 1/2 plus 2 over 2 is 3/2. Divide by 3/2, that's the same as multiplying by 2/3. Minus y to the 3/2 plus 2 over 2, that's 5 over 2. And divide by 5 over 2, that's the same as multiplying by 2 over 5. This is equal to minus 0.0004 root of 19.6 times t plus c. All right, so what we have is 6 times 2, 12 over 3. Let's simplify a bit more. We get 4y to the 3/2 minus 2 over 5 y to the 5/2 is equal to minus 0.0004 root of 19.6 times t plus c. Okay, so now we need to solve for the unknown constant c, the constant of integration. So we're going to apply the initial condition. At time 0, the tank is full. So there's 3 meters of fluid. The initial height of the fluid is 3 meters, which is the radius of the hemisphere, of course. So y of 0 is equal to 3. This means at time equals 0, the height of fluid in a tank is 3 meters. So we're going to use that to solve for c, for the constant c. All right, so what we have is 4 y to the 3/2 minus 2 over 5 y to the 5/2 is equal to minus 0.0004 root of 19.6 t plus c. We're going to substitute t equals 0, y equals 3 to solve for the unknown constant c. So we get 4 times y is 3, plug that in, 3 to the 3/2, keeping everything exact, minus 2 over 5 times 3 to the 5/2 is equal to, and substituting t equals 0 in here, well, the whole thing becomes 0, so it's 0 plus c. We solve for c. Let's plug it back in, and we have our implicit solution. It's implicit because we have an isolated y as a function of t. And I think in this case, it's extremely difficult to do that, so we can just leave our answer in implicit form. It contains the same information, the same relationship between the height y and t, which is time. 4y to the 3/2 minus 2 over 5 y to the 5/2 is equal to minus 0.0004 root of 19.6 times t plus c, which is going to be 4 times 3 to the 3/2 Let me write this at the bottom here, minus 2 over 5 times 3 to the 5 half. So we now have to solve for the time at which the tank is empty, such that all the water has exited the tank. So how do we do that? Well, we make y of t equal to 0 and solve for time. That's purely algebra. So when we make y equals 0, all of this is going to be 0. That helps. So we get 0 on the left-hand side is equal to, let me write that better, 0 is equal to minus 0.0004 root of 19.6 times t plus 4 times 3 to the 3 half minus 2 over 5 times 3 to the 5 half. We want to solve for t, so let's bring this expression here on the left-hand side, isolate the t. So we have 0.004 root of 19.6 times t is equal to 4 times 3 to the 3 half minus 2 over 5 times 3 to the 5 half. So it's very easy now to solve for time. Divide both sides by 0.0004 root of 19.6 and divide the right-hand side by the same quantity, 0.0004 root of 19.6. And these all cancel out. Cancel, 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 and we can solve for the time. All right, so what we have is 0.0004 root of 19.6 times t is equal to 4 times 3 to the 3 half minus 2 over 5 times 3 to the 5 half. And solving for t, we obtain 4 times 3 to the 3 half minus 2 over 5 times 3 to the 5 half divided by 0.0004 root of 19.6. This is a calculated ready answer. So if we decimalize this, we're going to get approximately 8,215.84 seconds. If we change that to hours, because 1 hour has 3,600 seconds in it, 1 hour is equal to 3,600 seconds, we're going to get t is equal to approximately 2.28 hours. That means that it will take approximately 2.28 hours for all the water to drain out of this hemispherical tank, according to Torricelli's law. All right, thanks.